You know, when you first start learning C, it's going to feel broken for about a week. I promise you, that is completely normal. In this explainer, we're going to break down exactly why, and more importantly, how to understand its error messages so you can power through that first week feeling way more confident.
Let's just start right here, because this is probably the most important thing to remember. If you're feeling a little lost or maybe even frustrated at first, you're not doing anything wrong. In fact, you're on the right track. We're about to walk through exactly why C feels so different from Python, and we'll give you a clear game plan for handling those infamous error messages. Okay, let's dive right into the single biggest difference between these two languages. Python is what we call an interpreted language, while C is a compiled one. And this one difference, this extra step, it changes absolutely everything about how you run your code and how you find your mistakes. So on the surface, the goal is exactly the same, right? Just print hello world. But just look at the C code on the right. There's a lot more going on, a lot more ceremony. You've got this hashtag include thing to bring in code libraries, this int main function, which is always the starting point of a C program, and of course all those curly braces and semicolons. All this extra structure is there because of that extra step C takes before it can even think about running. And this slide right here perfectly illustrates that extra step. With Python, it's simple. You type python hello.py, and the interpreter just reads it and runs it line by line right away. But with C, it's a two-step dance. First, you run GCC, that's the compiler, which translates your human-readable C code into a machine-readable program. Then you run that program you just created with /hello. So you might be asking, why on earth would we bother with this extra step? Well, it's all about a trade-off. C gives you just incredible speed in exchange for a little bit of that upfront simplicity. See, C programs are blazing fast because the compiler does all the heavy lifting and planning beforehand. The cost? When you make a mistake, the compiler catches it before the program ever runs, and its error messages can look pretty scary at first. Okay, so let's move on to our next big idea, which actually builds right on top of this. This is another place where C's need for a plan really shows up. It's what we call a statically typed language. In Python, you can just write x equals 5, and Python just figures it out. It knows on the fly that x is an integer. It's dynamic. But in C, you have to tell the compiler your entire plan right from the start. You have to declare the type of every single variable before you use it. You have to say, hey, this x is an int, or this y is a float for a decimal, or this is a char for a character. And this table shows you the reason why. This isn't just C being picky. When you declare int x, you're literally telling the compiler, hey, go reserve exactly 4 bytes of memory for this. A float also gets 4 bytes, a char gets 1. The compiler is meticulously planning the exact memory layout on the hardware before your program even starts. This pre-planning is a huge part of what makes C so incredibly fast. Oh, and a quick but super crucial point on syntax. You know how Python uses indentation to define blocks of code? Well, C doesn't care about whitespace at all. Instead, it uses curly braces to group things together, and a semicolon to end every single statement. Forgetting a semicolon is probably the first error you're going to make. We all do. And believe me, the compiler will definitely let you know about it. So, this whole idea of C giving you more direct control over the hardware, that leads us right into our next topic, memory management. Now, in Python, this is something you pretty much never have to think about. In C, well, it's now your job. Here's the key difference. Python has this amazing thing called a garbage collector. That's like a little Roomba for your memory. It automatically cleans up memory that you're not using anymore. It's safe, it's easy. C, on the other hand, hands you the keys to the car. You have to manually ask for memory with a function called malloc, and then you are personally responsible for giving it back when you're done, using free. So this is what that cycle looks like in practice. You ask the system for a chunk of memory that's big enough to hold, say, 10 integers. You should always check to make sure you actually got it. Then you can use that memory. And, this is the most important part, when you're all finished, you call free to return it to the system. If you forget to free your memory, you create what's called a memory leak. Now, for now, you don't need to write this from scratch. Just start to recognize the pattern. Ask, check, use, return. All right, we've gone over the big conceptual stuff. Now it's time for the most practical skill you are going to need this week, learning how to decode what the compiler is trying to tell you when things go wrong. I want you to think of the compiler not as an enemy, but as a
Very, very blunt friend.
So this is it. This is what a real error from the GCC compiler looks like. And yeah, I get it. At first glance, it just looks like a wall of confusing text. But I promise you, there is a system to reading it, and it's actually giving you all the clues you need to solve the puzzle.
Here is the process. Follow it every single time. First, just like with a Python error, you actually start at the bottom. Second, find the file name and the line number, in this case, hello.c, line 5. Third, go look at that line in your code, but, and this is the absolute key, also look at the line right before it. And finally, step 4, translate the compiler's message into plain English.
So let's translate this one. The compiler is basically saying, okay, I got to line 5, and right before I started to process the word return, I was expecting to see a semicolon, but I didn't. So where's the actual problem? It's not on line 5. It means the line before it, line 4, is missing its semicolon. See? It's a clue.
Here are a few more common translations you'll see. If the compiler says implicit declaration of function, that almost always means you forgot to hashtag include the right file at the top. If it says undeclared identifier, that means you tried to use a variable before you told C what type it was. And then there's the big one, segmentation fault. This one's different. It's not a compiler error. It's a crash that happens when your program is actually running. And it means your program tried to access a piece of memory it wasn't allowed to touch.
And I really want you to hear this loud and clear. Segmentation faults are going to happen. They are not going to break your computer. They are totally survivable. All that happens is your program crashes. That's it. You need to learn to see them as useful signals that are telling you where you went wrong, not as some kind of disaster.
Okay, so let's bring all this together now. I want you to try and reframe this whole experience. You are not starting over from square one. You're just learning a new dialect.
You already know the language of logic. You know programming. Python and C are just two different dialects for expressing those same core ideas. The concepts you know, variables, loops, functions, even memory, they're all the same. All that's changing is the specific syntax, the spelling and grammar, and the tools you use to get the job done.
So let's go back to that very first idea we talked about. C will feel broken. But is it really broken? Or is it just the normal, temporary discomfort of learning a new, more explicit, more powerful way of talking to the computer? That feeling isn't a sign that you're failing. It's the sign that you're learning.
And now, it's time for you to go write your first C program. You've got the concepts, you have a strategy for reading the errors, and you know what to expect. You are absolutely prepared for this. Good luck, and we'll see you in week 13.